Good morning, everyone. Today we're going to be taking a look at section 9.5. We're going to cycle back and look at our last way to graph, and we're looking at polar coordinates. We know how to graph in a Cartesian coordinate plane, the XY axis. We've graphed in parametric form, and now we're going to learn polar coordinates. And this is the last mode on your calculator that we're going to be talking about this year. We are going to be working on this next year in calculus, in Calc BC. For those taking AB, we'll see you again in Calc BC. But polar coordinates are really awesome. And eventually next week, we're going to be looking at their graphs and how cool those can be. So let's get into it. A polar coordinate system is the distance from a fixed point, and that point is called the pole. It's no longer the origin. We call this the pole when we're talking about polar coordinate system. You can also tell we don't have rectangles anymore. We have circles. And these are fixed distances away from the pole. These are R values, and that makes sense when you think about it in terms of circle, because in terms of a circle, an R value stands for a radius. So this has a unit length of R1, 2, 3, 4, and 5 on this picture. We have the polar axes, which is going across, and that starts at the pole and goes out. We also have this axis, which is no longer called the y, but that axis is called theta equals pi halves. And that makes sense when we talk about how we identify points in polar. Polar points are no longer talked about in terms of x, y. They are referenced in terms of r and theta. And r is the absolute value of the distance from the point P to the pole. And theta is the angle formed between the polar axes and our point. So you will not see these rays that I'm referring to right here. That's talking about this right here. Because when we're talking about polar, we're either talking about a graph or we're talking about a point. We're not talking about a ray. Those are not existing right now in our polar world. So we're looking at this angle right here, and just by estimation's sake, we're calling it pi fourths. So this has the ordered pair 2, pi fourths. 2 is the radius, it's the length away, and theta is pi fourths. Typically, when we're graphing points on the polar coordinate plane, we look for the angle first, and then we count outward in the R value. So we would find our angle pi fourths first, and then we would count out 1, 2. And I'll show you on the next graphs how much easier that is because of the guidelines that they set up for us to graph with. So we have two things to consider. One is if our R value is greater than 0, so if R is positive. And the second is when our R value is less than 0 or R value is negative. Theta is our angle in the standard position when our R value is positive. So here's our angle theta. We call that in the standard position. So it starts from our polar axes, counting counterclockwise. There's our angle theta. And then with our R value, that means we're counting out a certain length. So this has a value of R, and that allows us to put our point P. If our R value happens to be negative, that means we measure our angle theta, but then our point is located with an opposite ray. And if you can remember way back from geometry, opposite rays are just going 180 or pi units in the other direction. They have the exact same length. Oop. But are just going in the opposite direction. So that looks about the same length. So I'm going to put my point P here. And this one up here would have the point R theta, some R units out, theta units in that direction. And the one down here would be opposite of R, comma, theta. So let's take a look at an example of that. If I were to plot 4 comma 5 pi 6. I would want to find 5 pi 6 first, and then I'm going to count out from the pole 1, 2, 3, 4. That's my point P. If I were to plot -4, 5 pi 6, I would be finding 5 pi 6 first, and then counting 180 degrees the other direction. So 1, 2, 3, 4. So that gives me the angle still the same as 5 pi 6, just 4 units in the opposite direction, 4 radii out in the opposite direction. So why don't you pause your video and see if you can plot these 3 points, point A, B, and C. Just go ahead and touch your screen of where you think those would be located, and then we'll get you to check them in just a second. Notice that this is in radians. You will see polars with the exact same values all the way around, but with the degree measures instead. So now you have to think, where is 135 on the unit circle? So go ahead and pause your video. And take a look at that. So the points that you should have plotted, 135 is 3 pi fourths. So we're going 1 unit out in that direction. So I'm going to label that A. 2.5 and a negative pi 6. And we didn't specifically talk about this yet, but we have talked about this many times. If I have a negative angle, that means I'm going in the clockwise direction. So let me just take this one off. So we're going clockwise because we're starting at looking at the angle of negative pi 6. So we need to go 1 pi 6 down. And we are looking for 2.5 out. So 1, 2, that looks to be about 2.5. So we're going to label that B. And C is a combination of the two of them. So we want to go the opposite direction and a negative angle. So negative 120 would mean that I'm looking at 4 pi thirds for my angle. So starting at the polar axis, going down 4 pi thirds, and then I want to go backwards 3 radii. So 1, 2, 3. So there's another name that I can call that point that ends up in the exact same place. And all of these could have multiple names for that exact same point. This one turns out to have landed because we were looking at 4 pi thirds and going the opposite direction. We're looking at that angle right there. But as you can see, that also landed in the same spot as 3 comma 60 degrees, or 3 comma pi thirds. So when you're working with this, you should recognize that some of these are going to have more than one answer. So what I'd like you to do is, given the point of -2 pi thirds, find 4 different pairs that also represent the same point. I do not want you to put this into degrees. I want you to keep it in radians when you're writing all 4 of yours. So take a minute, pause the video. Let's plot the point first just to make sure we're all on the same page. We're looking at pi thirds as our angle, which means it is positive, or we're rotating counterclockwise. So there's pi thirds. And it's telling us that it wants us to go -2. So instead of going up 2, we need to go in the opposite direction. So pi thirds plus pi would give us 4 pi thirds. So we're going to be following this line. And we're going 1, 2. So there's my point. So tell us 4 other points that works for. So some of the straightforward ones that you could have gotten right away are just calling it by where it actually lands, 2 comma 4 pi thirds. That's probably the easiest one. We've also worked with coterminal angles, so another one that could be pretty easy is finding it in terms of going in the clockwise direction. So we would have a negative angle here. So 2 comma negative 2 pi thirds. And another one that we could do is I could go all the way around the circle in the negative direction and end up over here, but then use my negative r values to flip it back over there. So that would be a negative 2 comma 5, negative 5 pi thirds. And then we're looking at our rules of our coterminal angles. So why not keep it at 2, but then go multiple times around the circle, or keep it at negative 2 and go multiple times around the circle. So I could be looking at the point 2 comma 85 pi thirds. Now that's extreme. Most commonly, you're going to just want to add 6 pi thirds, so you're getting full all the way around the circle. But those are some options. Those are not all the ones that you could have come up with, but those are some options. So going back to that, you can have multiple representations of the same angle in terms of r and theta by looking at their coterminal angles. So if I have r and theta plus 2 pi k, this is just to get us full rotations around the circle. So we could have done that last one and added 6 pi thirds. So that would have gotten us at 7 pi thirds. Just a full rotation. So negative 2 comma 7 pi thirds. If I have a negative r value, what we're taking a look at is theta plus 2 pi 2k plus 1 pi units. And this is giving us an odd number because when I have a negative r value compared to the original angle, in order to get there, I have to add pi to it, 1 pi. So that means I can add 1 pi, 3 pi, 5 pi to manipulate this and get it at the exact same point. And those, of course, are where k are in integers. So let's go back to our representation of these and compare them, like I said, a little bit to what we've been doing for vectors and how we can translate them to rectangular points. And this is going to be something that's expected of you for the next couple years. If we have a polar point r theta, r is our radius from the pole, theta is our angle in terms of from the polar axes up, I can translate this into some x, y coordinate. X, of course, is our horizontal change, and y, of course, is our vertical change. So if we have the point x and y, I can name it in terms of r and theta and transpose it by putting the coordinate plane system on top of the polar system and show that they are going to get the exact same points. Likewise, I can also have a polar point and translate it into x, y coordinate points by taking a look at what we've got set up here. We've got our R value, we've got our theta, and what you can see is that this makes a nice right triangle, and we worked a lot with right triangles. So over here, this would be considered our height, which is our Y value. And it looks like it would be equivalent to R times the sine of theta. Let's see if we've got a theta in here. Nope, we don't need an emoji. So R times the sine of theta. And that, of course, comes from the fact that if we have a right triangle, we can set up the proportion that the sine of theta is equal to the ratio comparison of the height opposite the angle compared to the radius. So simply multiplying both sides by R yields us this equation. Likewise, if I want to find the adjacent side, I'm going to be setting up the cosine ratio. So the cosine of our angle theta is the ratio of x over r, the adjacent side over the hypotenuse, which is our r value, which is the radius, multiplying both sides. That gives us x equals r times the cosine of theta. And this is how we're going to be able to convert from polar to rectangular and rectangular to polar using these two equations. So it says find the rectangular coordinates for each of these pairs. One's an angle in radians and one's an angle in degrees. So let's just go ahead and plot that point first. So 4 pi thirds. So 1 pi third, 2 pi thirds, 3 pi thirds, 4 pi thirds down here. And then we're looking at going -2. So 1, 2. So we have our R value, and you can rewrite this as the actual point that you get, or you can include these values in there and watch it manipulate itself. So I can evaluate this at the point 2 comma pi thirds, and I'm going to choose to do that just so everything's in the first quadrant, and it just makes it a slightly easier. So let's do this really quick and see if we can get this a little bit faster. Maybe not. So x equals the cosine. Oop. We'll attach it on the end. Cosine of pi thirds. And we're going to be multiplying this by 2 because that's our R value. Always a good time with digital learning. So cosine of pi thirds, of course, is 1/2. So we've got 1/2 times our R value of 2. That means our X value is 1. We're going to try that for our Y. We're going to have our R value times the sine of pi thirds. So So we've got 2 times the square root of 3 over 2, which leaves us with the square root of 3. No need to put this in your calculator. No need to approximate anything. We like exact answers. So this gives us the ordered pair, 1 comma square root of 3. And that's our rectangular coordinate. If I were to put an XY coordinate plane right on top of it, that point that's already plotted would hit at this point. So let's try that again for this one. We've got this in degrees right now. So 250 . So we've got 180, we've got 210, we've got 225. Here's 270. So we're looking around here. So that's 15 degrees away. And at 2.5, so 2.5, there's our point Q. So X is going to be equal to 2.5 times the cosine of 250 degrees, and y is going to be equal to 2.5 times the sine of 250 degrees. So remember that that is not on the unit circle. We're going to grab our calculator and make sure it's in degree mode because this is in degrees. And we're going to take 2.5 times the cosine of 250 and 2.5 times the sine of 250. And take a look at your calculator. Make sure that both of your answers are negative. Because we are in Q3, we want to make sure that we're getting the right answer. We're going to approximate it to 3 decimal places. So our X value is the opposite of 0.855 approximately. And our Y value is at negative 2.349. So those are pretty straightforward. So if you had the rectangular coordinates, how do you think you would find the polar coordinates? So in order to find the polar coordinates, we need to find some R value, and we need to find our theta. So if we're switching from rectangular to polar, we're going to use these. We're going to take and set up the ratio of the tangent of theta is equal to y over x. And we're going to use the fact that we created a right triangle. So r squared must equal x squared plus y squared. I starred tangent of theta because you're really taking theta equals your tangent inverse. So please don't cheat on that notation, but we're looking for the tangent inverse of y over x. And remember, if you're using inverses, you need to keep in mind dad. So tangent is only going to give you something of that in terms of the first and fourth quadrant, of course, talking about the positive and negative angle there. So let's take a look at one of those examples before you jump into that. We have the polar coordinate of negative square root of 2, or we're trying to create the polar coordinate for our rectangular coordinate, negative square root 2 with 2. So this is our x, this is our y. So that means our r squared value is the opposite of the square root of 2 squared plus the square root of 2 squared, which means r squared is 2 plus 2, which of course is 4. And this also leads into how our R values can be positive and negative. So this means R can be positive or negative too, because we're taking the square root of both sides. And we'll play around with this in terms of our angle. So we're going to let theta equal the tangent inverse of the ratio of the y to the x. So positive square root of 2 over the opposite of the square root of 2. So that gives us -1. And that would be -pi4. But I know that this is not in quadrant 4. This point is in quadrant 2. So that means I need to manipulate my angle that I got for my tangent inverse by either adding or subtracting pi units, because I need it to go to the other quadrant. So this can give us 3pi4. If I want to talk about it in terms of this angle of 3pi4, then I need my positive R value. So I could have 2, 3pi4. But think about it in terms of the angle that we got, which was -pi4. So -pi4 would be down here. And simply putting a -2 in front of that for the R value would also get you to the same point, same location. When you're doing this, though, I'd like you to try to write it in terms of the positive angle so that you have that practice of putting those values in. So this is what you're going to be doing for your homework tonight. Please let me know if you guys have questions, and I will talk with you all later.